Next up is Henry Shiu, and he'll talk to us about the Wind Collaborative.
So Jerry asked us to focus on one specific concept, and I have to apologize to you, Jerry, because I missed that memo. But I also want to thank Jerry for pulling this panel together, and in doing so, recognizing that while it's useful to talk about renewables collectively, all the renewables are in different places in terms of deployment and research, so it's very good to have all of our different perspectives brought together, so thank you for that. So what I want to do today is highlight some of the research efforts that we've had going on here at UC Davis, talk about some of the ones that we think that will be emerging and are very, very important, and how that fits in with both state and federal goals for increased penetration of renewables. There we go. So we've been at the wind power research game for quite a while now, more than 20 years here at UC Davis. I want to extend apologies from our directors, faculty members Case Van Dam and Bruce White, who couldn't be here today. Behind them are a small army of graduate students, many of which I've listed here. In particular, I want to point out our past graduate students. Many of them have graduated and gone on to continue to work in wind, in the industry, in national labs, at utilities. And for us, that's a big source of pride. It's a metric of success for our group. Happily for us, they have also continued on to become collaborators, a few more which I've listed on the bottom. So I'm not going to spend a lot of time on these slides. Let it just be known that wind energy as an industry is doing very well, both globally and here in the United States. Here in the U.S., I have this graph up to 2010. At the end of 2010, last year, the U.S. had installed yet another 5 gigawatts of wind, so we're up to 40 gigawatts of wind in the U.S. right now. Currently, we're only surpassed by China, which has 41, 42, and frankly, if you add up the numbers up to April, I'm not sure who's ahead, and it doesn't really matter anyway. Just a brief slide about wind turbine technology. So on the left axis of the graph, that's the rotor size of wind turbines in meters. So turbines have gotten bigger and bigger as the years have gone by, and there's very distinct economic reasons for it. When you go higher, you get to reach better wind resources. Also, typically, there's a benefit in terms of balance of plant. It's cheaper to have one big foundation, one road, one interconnection than have two smaller ones. And this increase and continued increase in growth, this graph is a little bit old, but it's actually pretty much spot on. This increase in growth is driving some of the research that we're doing here today. So a few years ago, we in the collaborative sat down and tried to bring a little bit of order to the work that we've been doing in past years. And we made this diagram. It's a bit of an eye chart, and I apologize for that. I'll go into details on the more important points in just a little bit. But what we tried to identify was, first, what does the industry need? And when I say industry, I don't just mean the commercial industry, but what does the world need? What does the United States as a country need? And fortunately for us, we've established very good rapport with industry, with national labs, with DOE, with utilities, with grid operators, so we feel that we have a pretty good understanding of that. Helping everybody along, in 2008, the DOE released their 20% wind energy by 2030. That's more than just stating that we really would like to do it. They actually did a very nice catalog of the technical, the environmental, the market hurdles that have to be addressed if that's really going to happen. And that really has become a blueprint for research in wind across the entire country. Here within the state, well, we're here in California, and we're also interested, well, what does the state of California specifically need? Here in California, research has been driven primarily by the Renewables Portfolio Standard and to a lesser extent in wind by AB 32. In addressing the RPS and bringing it into action, the CEC, the PUC, the utilities, CalISO, many other entities have done a very good job of driving research over the last few years. And then finally, of course, in trying to identify what we need to work on, what we want to work on, we also had to take into account what we're good at. What can we do to leverage our core strengths and knowledge? So I've highlighted two areas over here, blades and rotors and a subsection of grid integration. I'll get into those in a little bit. And those are kind of what I feel are our core areas of strength. We've been at this for a very long time. We have a very good feel for it. And then also, I'll come back to these yellow areas in a little bit. Those are things that I think will be coming around the corner very shortly now, or have already come around the corner, but for some reason, most people aren't looking at them. So first, advanced blades and rotors. In terms of conversion technology, wind power is very, very mature. That doesn't mean there isn't room for improvement. When we look at making better blades, smarter blades, and smarter rotors, predictions have shown that potentially you have 8% to 20%, 22% reduction in cost of energy possible. And you do that by increasing capacity factor, decreasing the capital costs, and increasing reliability. One mechanism for doing that is doing some sort of control of aerodynamic forces in blades. So that means that you are affecting the energy production at the onset of the energy capture, when the air first reaches the wind turbine. And the potential for that is phenomenal. So if you can manage aerodynamic forces and loads, you can reduce structural loads on the machines. That means you can make lighter turbines. Lighter turbines mean cheaper turbines. At the same time, it goes beyond that too. You can use it to improve power quality so that the electrons coming out of the generators are more compatible with grid operations. And potentially you can also use it to more for grid operation applications. So I'll kind of forego the integral over here, but the lift equation very nicely shows all the mechanisms that are available for aerodynamic forces and loads. And there's basically two broad categories that you can look at in harnessing that. Passive load control and active load control. We've had our hand in both. I'm not going to go into passive load control. We've had some extensive work on that, which was kind of culminated with a field test of a utility scale turbine, which I have a nice picture over here. But I will spend just a few more seconds to talk about active load control in the following slide. So the idea here is that you can embed devices, sensors, controls into blades, onto rotors, and thereby control the aerodynamic forces that are being absorbed by the machine. There's two mechanisms that we've looked at. First, I'll tell you a little bit about microtabs. The concept there is that you have these very small tabs. You can see them on the far right, those little tabs that are sticking in and out, sticking up and down out of the trailing edge of the blade. And those small devices actually have huge aerodynamic global control over the blade. And doing so, again, you can, for example, have a gust incoming to a wind turbine on a traditional dumb blade. That gust would hit the blade. The machine would have to be designed heavy enough, strong enough to be able to absorb that load. Here, potentially, you could have a lighter machine, and you could have the tabs actuate, reduce the aerodynamic loads. At the same time, that reduces the spike in power, which would cause a spike in power output going out to the grid too. We've done a variety of studies on this, CFD, some results that were shown on the left, which I won't go into in any detail. Wind tunnel studies, looking at both how the aero and the structural dynamics interact, and then this has also gone into field testing too. Currently, we're also starting looking at circulation control, so instead of having physical little devices that are poking in and out of the blades, using blowing and suction of air to accomplish the same thing. So shifting gears a little bit, I want to talk a little bit about forecasting. When you look at integration studies, any of the integration studies that are out there, whether it be the California IAP or any of the large-scale interconnect integration studies that came out for the Eastern and Western Interconnect last year, or even for a very, very small control area like the island of Hawaii, which just completed a study last year. Forecasting is listed as one of the most critical technologies that needs to happen if you want to integrate high penetrations of renewables, of wind specifically. We have quite a bit of experience with this, both in terms of developing better forecast. Dave Lubitz and Bruce White, my second bullet point here, conducted a good study a few years ago, coupling wind tunnel with computational weather modeling. Just recently, we completed a study with Jerry looking at the state of the art in forecasting, where things are currently now in the industry. And there's been a lot of interest in hour ahead and day ahead forecasts. Obviously, that's very interesting, very important to the grid operators. They want to know how they're going to allocate their unit commitment and their load following resources a day ahead and an hour ahead. But more and more recently, we've been hearing about intra-hour wind forecasting. So here in this very busy graph, you might be able to see there's a very thin gray line over there. So there's a thicker gray line, there's a thin gray line to the left of that, and that's a 10-minute interval. And this is for a small local wind plant around here. And within that 10-minute period, all 8 of their wind turbines went from generating 3,000 megawatts each to just about 0. So that's pretty much a grid operator's nightmare scenario. And I really want to emphasize this happens very, very, very rarely. But it does happen, and telling your grid operator that doesn't happen very often does not help them sleep at night at all. So there's been a lot of interest in understanding how often these happen and whether or not they can be predicted, because this has a significant impact on what's called regulation reserves. And we have a couple studies that will be emerging with the CEC and CALISO coming up. Small distributed urban wind power, we have a few efforts that are going on there, including developing some very user-friendly tools that are accessible via the web for doing economic assessment of wind power for end users and consumers. We also have a bunch of efforts going on in urban wind, mostly with the city of San Francisco. A couple other things I want to point out. These are areas that I said I think they're emerging and they're the things we don't want to miss out on in the coming 3 to 5 years. Offshore. So if you've ever seen a wind map of California, that's the map to the right on the screen. You can actually see California doesn't have a very good wind resource. I think we've done a very good job of taking advantage of what we have terrestrially, but if you look off the coast, on the left side of that image, there is a huge amount of wind that's out there, and that's a good, clean, strong, relatively predictable wind resource with lots and lots of development hurdles. It's been estimated that gross, there's 4 terawatts of power to be harnessed out there offshore the United States. NREL and DOE specifically has thrown a lot of resources into this recently, and for 2012 they're predicted to commit almost 60% of their budget toward offshore wind resources. Again, there's a host of resources, a host of problems and issues that come along with it, and there are a few California-specific ones too, so I'm just going to jump to my last bullet point over there. Here in California, we have a continental shelf. That means that in a in a big hurry, when you start heading off the coast, it gets really, really deep. That actually isn't the case in most of the rest of the coastline of the United States. So a lot of the research that's going to happen is going to look into shallow water mooring, or shallow water foundations and anchors. And that's going to be very, very different than what's going to happen here in California. So if we want to figure out where we're going to fit in with offshore, we need to start thinking about those things now and committing some research to it. Also, California is legendary for its difficult permitting environment, which has both its pluses and minuses, and the developers here in wind in California know well that just for terrestrial applications. When you start heading out into the water, then you're thinking about California Coastal Commission, the Bureau of Ocean Energy Management, and some other acronym which I can't remember, and just a host of other alphabet soup. So it's going to be very, very difficult, and frankly, it would behoove us to start thinking about that now instead of waiting until there's offshore that's trying to get into California years down the line. Asset optimization and wake effects, investigating underperformance. There's been anecdotal evidence that wind plants across the country are underperforming. So just very, very dramatically, I did some back-of-the-envelope calculations. If you have a 150 megawatt plant, over a year, you're losing potentially 50 gigawatt hours of energy, $4 million if you value that energy at 8 cents per kilowatt hour. That's a lot of electrons that you're leaving on the table, not to mention a lot of dollars that you're leaving on the table. If you try to figure out what's going on from an owner's perspective, the guys who put the wind plant in for you, the developers, and the guys who made the turbines will just point their fingers at each other, which isn't very terribly useful for you. But again, we are potentially leaving free energy on the table. So asset optimization, I think, is an area where we can look at the plants that we have out there, the turbines that we have out there, and do better. Also, wake effects, the influence of a turbine behind another turbine. There's been some research going on in that. A lot of that has been focused on offshore applications and in plains, in the Great Plains, because there's expectations for large penetrations of wind in the Midwest. Here in California, though, we have complex terrain. Potentially, we're looking at a whole lot of turbines going into Tehachapi. Those are mountainous ridges, very, very different from any of the wake effects that are studied anywhere else in the United States or in Europe for that matter. And if we want to make the most of all that capacity that's going in, potentially 6.5 gigawatts of wind going into Tehachapi, we're going to need a better understanding of that. So final thoughts is, once again, wind, I think the industry is in a very good place. It's a very viable industry, but there's still a lot that we can do to make it better. Thank you.